Greetings to all my tech heads out there in the KevTechify Nation, and if you're new here, welcome. In this episode, we're going to look at confidentiality. We'll be discussing data confidentiality, symmetric encryption, asymmetric encryption, authentication, integrity, and then finally we'll look at the Diffie-Hellman algorithm. This episode is part of my series on network security for the Cisco Certified Network Associate, or CCNA. I'm Kevin, here at KevTechify. Let's get this adventure started. Symmetric encryption, such as Data Encryption Standard, DES, Triple DES, or AES, Advanced Encryption Standard, are based on the premise that each communicating party knows a pre-shared key. Data confidentiality can also be ensured using asymmetric algorithms, including the Rivas Ciphers, Adelman, RSA, and the Public Key Infrastructure, PKI. The figure here highlights some of the differences between symmetric and asymmetric encryption. When we look at symmetric encryption, they use the same key to encrypt and decrypt the data. Key lengths are shorter. A lot of times we see 40 to 256 bytes. Lately, I've been also seeing some 512 with this. It is much faster than asymmetric encryption. And finally, it's commonly used for encrypting bulk data such as your VPN traffic. Asymmetric encryption is a little bit different. It uses different keys to encrypt your data for the encrypting and decrypting process. Key lengths are a lot longer, 512 bits all the way up to 4096. The calculation of getting or encrypting your data usually is a lot slower, so it takes more time. And asymmetric encryption typically is used for quick data transactions such as HTTPS, like when you access your bank or private information across the internet. Symmetric algorithms use the same pre-shared key to encrypt and decrypt the data. A pre-shared key, also called the secret key, is known by the sender and receiver before any encrypted communications can take place. So they have to know that key before they start passing data. Here we have an example. A person is going to send some money across the network. These two people, we'll call one Alice over here, and then Bob over here. So Alice and Bob have identical keys to that single padlock. Now, these keys were exchanged prior to sending any secret messages. Alice writes a secret message and puts it in a small box that she locks using the padlock with her key. So she writes a secret message. She puts in $1,000 into this box where she locks it. She encrypts that message. She then mails that box to Bob. Goes to the post office, puts it in there, sends it there. The message is safely locked inside the box as the box makes it through the post office system. Now, when Bob receives the box, he uses his key to unlock the padlock and retrieve the message. It's that secret message. Maybe it was that $1,000. Whatever Alice put in there, Bob can now get. And Bob can use that same box and padlock to send a secret reply back to Alice. Symmetric encryption algorithms are sometimes classified either as block cipher or stream cipher. Here we have block ciphers. Block ciphers transform a fixed length block of data of plain text into a common block of ciphertext of either 64 or 128 bits long. Now, common block ciphers include DES, which is a 64 block size, and AES, which is 128 block size. And so we have 64 bits here. This is DES. Every 64 bits then gets encrypted and sent across there. Stream ciphers encrypt plain text 1 byte or 1 bit at a time. Stream ciphers are basically a block cipher with a block size of 1 bit or byte. Stream ciphers are typically faster than block ciphers because data is continuously encrypted. There are several well-known symmetric encryption algorithms. First one here is Data Encryption Standard, also known as DES, DES. This is a legacy symmetric encryption algorithm. It uses a short key length that makes it insecure for most current uses. Now, once again, notice we're saying it's a legacy symmetric encryption. Legacy. Legacy means you're using it on older equipment that does not support newer standards. Don't use DES unless the equipment only supports DES. Use something else. Then we have what's referred to as triple DES, 3DES. This is a replacement for DES, and it repeats that DES algorithm, that data encryption standard algorithm process 3 times. It should be avoided if possible, as it's scheduled to be retired in 2023. Now, if it implemented, use very short key lifetimes. Use short key lifetimes if you're using triple DES. Next one we have is Advanced Encryption Standard, also known as AES. AES is a popular and recommended symmetric encryption algorithm. It offers a combination of 128, 192, and 256-bit keys to encrypt 128, 192, 256-bit long data blocks. So the keys can be 128-bit, 192, 256, and then it encrypts on a block basis, and those blocks can either be 128-bit, 192-bit, or 256-bit long blocks. The next one we have is Software Optimized Encryption Algorithm, also known as SEAL. SEAL is a faster alternative symmetric encryption algorithm to the Advanced Encryption Standard, AES. So it's a faster alternative. SEAL is a stream cipher that uses a 160-bit encryption key and has lower impact on your CPU compared to other software-based algorithms. And then finally, we have the Rivas Ciphers, also known as RC, and that's a series of algorithms. Now, this algorithm was developed by Ron Rivas. Several variations have been developed, but RC4 was the most prevalent in use. RC4 is a stream cipher that was used to secure web traffic. It's been found to have multiple vulnerabilities which have made it insecure. RC4 should not be used. Asymmetric algorithms, also called public key algorithms, are designed so that the key that is used for encryption is different than the key that is used for decryption. The decryption key cannot, in any reasonable amount of time, be calculated from the encryption key and vice versa. There are some examples of protocols that use asymmetric key algorithms. First one here is the Internet Key Exchange, also known as IKE. This fundamental component of IPsec VPNs. The second one is Secure Socket Layers, or SSL. This is now implemented as the standard transport layer security, or TLS. Next one here is Secure Shell, also known as SSH. This protocol provides secure remote access connection to network devices. And then finally, we have Pretty Good Privacy, also known as PGP. This computer program provides cryptographic privacy and authentication. Here are some of the more popular asymmetric encryption algorithms. First one we have here is the Diffie-Hellman, also referred to as the DH. It's got different key lengths varying from 512 all the way up to 4096. The Diffie-Hellman algorithm allows two parties to agree on a key that they can use to encrypt messages they want to send to each other. The security of this algorithm depends upon the assumption that it's easy to raise a number to a certain power, but difficult to compute which power was used given that number and the outcome. The next one here is the digital security standard, or DSS, and the digital security algorithm, the DSA. They have key lengths between 512 to 1024 bits. The DSS specifies the digital signature algorithm, the DSA, as the algorithm for digital signatures. Digital signature algorithm here is a public key algorithm based on the El-Gamal signature scheme, which we'll talk about here in a second. Signature creation speed is similar to RSA, but is 10 to 40 times slower for verification. Then we have the Rivas Ciphers Adelman encryption, also known as RSA. Here, key lengths typically go from 512 bits to 2048 bits, 2048 bits. RSA is for public key cryptography that is based on the current difficulty of factoring very large numbers. It is the first algorithm known to be suitable for signing as well as encryption. It is widely used in electronic commerce protocols and is believed to be secure given sufficiently long keys and use of up-to-date implementations. Once again, notice the key, sufficiently long keys. Then we have the El-Gamal. This key length here is typically, once again, 512 to 1024 bits long. El-Gamal is an asymmetric key encryption algorithm for public key cryptography, which is based on the Diffie-Hellman key agreement. A disadvantage of the El-Gamal system is that the encrypted message becomes very big, about twice the size of the original message. For this reason, it is only used for small messages such as secret keys. And then finally, we have the elliptical curve techniques. The key length here is typically 224 bits or higher. The elliptical curve cryptography can be used to adapt many cryptographic algorithms, such as the Diffie-Hellman or the El-Gamal. The main advantage of the elliptical curve cryptography is that keys can be much smaller. I hope you liked this episode on confidentiality. Leave a comment about what you think about confidentiality. You can visit my website at KevTechify.com for all of my details and how to get these episodes in video and podcast form. For confidentiality, the process can be summed up with this formula, where we're looking at public key to do the encrypting, the public key to do decrypting. That gives us our confidentiality. When the public key is used to encrypt the data, the private key must be used to decrypt that data. Only one host has the private key, therefore confidentiality is achieved. All this starts off with is over here. Alice requests Bob's public key. So Alice says, "Can I get your public key, please?" Bob says, "Okay, here's my public key," sends it to Alice. Then Alice uses Bob's keys. So once again, that's Bob's keys that Alice requested. Then Alice combines the key with the message. So this is your message here. Runs it through our encryption algorithm and gets our encrypted text. Alice then sends Bob that encrypted text. So it goes over to Bob. Bob then takes his private key, because once again, remember, it's asymmetric. So Bob can't use his public key to decrypt it. He needs to use the private key to decrypt it. So Bob takes the encrypted text with his private key, runs it through the algorithm, and gets that message that Alice sent. So that's how we get our message, using the private key for decryption. The authentication objective of asymmetric algorithms is initiated when the encryption process is started with a private key. The process here can be summarized. Notice we're starting with the private key to do our encryption. Then we're using the public key to do our decryption, and that will give us our authentication. And so how this starts over here is Alice encrypts a message with her private key. So Alice gets a message here. Once again, this is the message. Encrypts it with her private key. So they takes her private key, runs it through an encryption algorithm, gets encrypted text. So that's how we get our encrypted text. Now, in order to authenticate the message, Bob requests Alice's private key. So Bob over here says, hey, can I get your public key? Public key is then sent to Bob. Once Bob gets that, Bob takes that encrypted text that Alice will send them. So the encrypted text gets sent to Bob. We also got Alice's private key that we sent there. We take the encrypted text and the public key. Sorry, I meant to say public key. Alice sent the public key because you never send a private key. You always send your public key. You run it through our encryption algorithm, and then you get your message. You look at that message, and this then authenticates that Alice is who she says she is because of how we went through that process first of having the private key to do the encryption and then the public key to decrypt it. Combining two asymmetric encryption processes provides message confidentiality, authentication, and integrity. We're going to go through an example here that's going to illustrate this process. In this example, a message will be ciphered using Bob's public key, and ciphered hash will be encrypted using Alice's private key to provide confidentiality, authenticity, and integrity. Now, what we're going to do here is Alice wants to send Bob a message. So that's where we're starting. And she wants to make sure that only Bob can read the document. So what really happened here is Alice wants to send a message to Bob, confidentiality. Nobody else can read it. And make sure it's only Bob. Alice uses the public key of Bob. So this is Bob's public key. So right here we have Alice at her computer. We have Bob's public key. So we had to ask Bob for his public key. And what we're going to do is we're going to cipher that message. We're going to take the plain text, our message right here, take Bob's public key, run it through an encryption algorithm, and we're going to get our encrypted text. Alice also wants to ensure message authentication and integrity. So what we do here is authentication ensures Bob that the document was sent by Alice, and integrity ensures that it was not modified. And what happens here is Alice uses her private key to cipher a hash of the message. Alice then sends the encrypted message with its encrypted hash to Bob. And so what happens here is Alice then she hashes the message, takes that hash and encrypts it with her private key, runs it through an encryption algorithm, gets you some encrypted information. The encrypted hash with that. After Alice does the encryption of the message, does the encryption of the hash of the message, she sends all that information over to Bob. Now Bob has to go through and look and decrypt all of these messages. First thing we're going to do here is Bob uses Alice's public key to verify the message was not modified. So we take that encrypted hash. So that was the hash value of the message. We use Alice's public key because Alice used her private key to encrypt it. So we take that encrypted hash, Alice's public key, run it through our decryption algorithm, and we get the hash. Now we can calculate the hash, compare values, and if they match, we then know that the message was not modified. The second step Bob needs to do is he's going to use his private key. So Bob uses his private key to unencrypt the text. So this is the encrypted text from Alice. We combine it with Bob's private key, run it through our decryption algorithm, and we get our plain text. This will give Bob the original message from Alice. Diffie-Hellman is an asymmetric mathematical algorithm that allows two computers to generate an identical shared secret without ever having communicated before. The new shared key is never actually exchanged between the sender and receiver. However, because both parties know it, the key can be used by an encryption algorithm to encrypt traffic between the two systems. Now, two examples of where The instance of this Diffie-Hellman commonly used is data exchange using an IPsec VPN, so IPsec VPN, and also when SSH data is exchanged in SSH. Here's an example. Now, instead of using complex numbers to show you how the Diffie-Hellman works through this process, we use colors. And first thing that has to happen is Bob and Alice have to agree on a starting color. So they agree on this starting color. What happens with the starting color is Alice and Bob both have a secret color. So the agreed upon color here is yellow. Both Bob and Alice agree upon yellow. Bob and Alice also have a secret color. Alice's secret color is red. Bob's secret color here is blue. What we do is we take and combine the agreed upon color and combine it with the secret color. So Alice's yellow and red, this makes orange. And for Bob, the agreed upon color is yellow. His secret color is blue. That will give us green. Now, these combined colors, these are public colors. These are the colors that they will show everybody who looks at them, and they'll say, hey, this color is orange. This color is green. Because it's shown to everybody, Alice can see what Bob's public color is. So Bob's public color is green. Alice knows that. Bob then can see Alice's public color, which is orange. So now Bob knows what the public color is then. We add in our secret colors. Once again, Alice's was red. Bob's was blue. We combine the public color of the other person with our secret color, and we get a final color. So we combine green and red, and that will give us tan for Alice. And then for Bob, we take orange and blue, and that will give us tan also. Now, this is an overly simplified way of how it works, but notice they never exchange a key. All they do here is they see each other's public colors. They see each other's colors, and because of what they see as the public colors, they combine it with their private colors, they can get to their messages. Diffie-Hellman uses different DH groups to determine the strength of the key that is used in the key agreement process. The higher the group number, the more secure, but it also requires additional times to compute that key. Here are the groups that are supported by the Cisco iOS and their associated prime number values. We can see that we have groups 1, 2, 5, 14, 15, and 16. Group 1 is 768, all the way down to group 16 is 4096 bits long. These are the groups that are supported. Yes, there's a group 3 and 4 in there, but it didn't provide any advance in security, so there was no need to support it. Cisco chose not to support those. Same thing with 6 through 13. Didn't really provide any advances, so Cisco decided not to support those. So once again, the Diffie-Hellman groups are 1, 2, 5, 14, 15, and 16. It was my pleasure to provide you with this wonderful episode on confidentiality. If you like this episode and you got value out of it, and of course, depending upon what platform you're using, please click that like button, give a 5-star rating, leave a comment. This all helps me bring you more great content. Please take a minute to subscribe to my channel. All of my socials and contact information are on my website, KevTechify.com. There you can find out how to get all these episodes in video and podcast form. In the upper right is my playlist for my series on network security for the CCNA. In the bottom right is one of my favorite videos that I linked just for you. Thank you so much for watching this episode of my series on network security. Once again, I'm Kevin, and this is KevTechify. I'll see you next time for another great adventure.